We stopped here last time. So selected problem. Already chapter 17 finished. We stop here in selected problem. Let's first the problem. Let's read together and try to understand together and solve it. An orthogonal machining test for steel material, for cutting steel material. The following data were obtained. This is a given. This is a given result. Let me tell you, this is a given in a problem. Those are the given in the problem, and given is a cutting speed. Given cutting speed is a cutting speed. This one, right? I hope you remember. Cutting speed is given. Cutting width or width of cut is given. Width of cut, which is exactly is the depth of cut as well. And the formal chip thickness TO is given. Cutting ratio R is given. Alpha rake angle is given. Shear stress is given. Shear stress. He gave me here shear stress. And the coefficient of friction mu is given. This is the item given in a problem. And he asking for some question here. Can you see that? Compute the following A, B, C, D until the end. First question is what is the friction angle? Friction angle is beta. Friction angle is beta. So beta, need to know what is the beta. Beta is a friction angle. So tan beta equal to F divided by N. Tan beta, then friction angle. This is the first question. First question, what is the friction angle? Friction angle, to remind you, friction angle is beta. Tan beta equal to F divided by N or mu. Mu is tan beta. Right, so tan beta mu. Mu is given, coefficient of friction here. This is a coefficient mu. This is a mu, coefficient of friction is 0.5 equal to tan beta. Then we can obtain beta. Beta equal to tan minus 1 mu, which is 0.5. Then you get beta, right? Second question, what is a shear plane angle phi? What is a phi? We need to know what is a phi. Second question. Phi, what is a phi? Shear plane angle. Phi. Okay, to obtain phi, we use a chip. Actually, there are many ways. You have here alpha is known. We know alpha and we know beta. We can use alpha and beta. We can obtain phi, but he said that use a chip thickness ratio equation. Chip thickness ratio equation, which is tan alpha equal to 1 here. This is the equation. Then we can use equation tan phi equal to r cosine alpha divided by 1 minus r sine alpha. So this is the equation. So in this way you can obtain phi, which is the shear plane angle. Velocity of shear. Velocity of shear, we know V. V is given. We need to know what is the velocity of shear. Velocity of shear, this is the velocity of shear. Then we need to know, then V is given, we need to know Vs. Then you need to apply the velocity triangle, and when you apply velocity triangle, you can get Vs, and also you can get Vc as well. So you can get Vs and also Vc as well. And then you need the force, Fs, Fc, and Ft. Shear stress is given. Then Fs here we can obtain as a function of shear stress divided by As. You need to obtain As, and then you have shear stress, then you can get the shear force. Fc and Ft you can obtain from the Merchant circle. If you know Fs, you obtain as a function of R, Fc as a function of R, Ft as a function of R, and then you can obtain whatever Fc and Ft as a function of or with respect to Fs, which is known. Power consumption in a primary shear zone. This is a primary shear zone. This is a primary shear zone. Primary shear zone meaning the shear. So needs the power, the shear power, which is FSVS. We need the power to overcome the friction. Power to overcome the friction meaning here, which is F friction multiplied by Vc. And we need material removal rate. Material removal rate VFD. Let's see the solution one by one, as I told you. First, what is a mu? Mu equal to tan beta. Sorry, mu is given. We need beta. Mu equal to tan beta. Mean beta equal to tan minus 1 mu. tan minus 1 mu, then mu is given, then you get beta. Tan phi equal to r cosine alpha divided by 1 minus r sine alpha. R and alpha given, then you can obtain phi, then phi can be obtained. Next, we need to know what is the Vs. We know V is given, we need to know what is the Vs. Then V divided by Vs from the velocity triangle. You apply velocity triangle. This is the Vs, this is the V, this is the Vc, right? Can you see that? This is phi, this is 90 minus alpha, this is 90 minus phi plus alpha. Then you know that Vs divided by sine this angle equal to V divided by sine this angle. Then you obtain Vs divided by V equal to cosine alpha divided by cosine phi minus alpha. Then alpha we know and phi we know. Then you can obtain Vs. Vc also we can obtain Vc. Vc divided by sine phi equal to any of these two, because now both are known, divided by the cosine of the corresponding angle. In this way you can obtain Vs and also can obtain Vc. Next is shear strain. Shear strain is equation is gamma equal to tan phi minus alpha plus cotan phi. Alpha and phi we know, then you can obtain. And then we need EF, Fs. We need to obtain Fs, shear stress. Shear stress. We know the shear stress we know is 400. This one is given. Shear stress is given, which is 400. We need to know the shear force. Shear force can be obtained as tau multiplied by As. Then we need to obtain As. As can be obtained as WTO sine phi. TO we know, W also we know, phi we know. Then you can obtain As. Then you can obtain the shear force. If you obtain shear force, actually you can use the Merchant circle. If you obtain Fs we know, then we need Fc and Ft. Fc and Ft. So we know Fs now, we need to obtain Fc and we need to obtain Ft. Then obtain the relation Fs with R. Fs with R. Fs equal to R cosine this angle, which is phi, plus beta minus alpha. This one beta minus alpha. Let me just tell you. I hope you remember. Actually, this is really very important. You must know this one. This one is beta minus alpha. And this one also is beta minus alpha. So this angle equal to this angle, which is beta minus alpha. So this one beta minus alpha. Then Fs equal to R cosine beta minus alpha. Then Fs equal to R cosine beta minus alpha. Fc equal to R. This one angle is R cosine beta minus alpha. R cosine beta minus alpha. Ft also equal to R cosine beta minus alpha. This is the equation you can obtain from the Merchant circle. If you need to get Fc, then Fc equal to Fs cosine beta minus alpha divided by cosine phi plus beta minus alpha. Then you can just get Fc, and also you can just get Ft as a function of Fc, because Fc equal to R cosine beta minus alpha, Ft equal to R sine beta minus alpha. You divide, then R lowers the R, then you get Ft equal to Fc tan sine divided by cosine tan beta minus alpha. Then you can obtain. If you have any question, you stop me anytime, no problem. This is the power consumption in the primary shear zone. Primary shear zone, this is the primary shear zone, right? Power consumption primary shear. This is the primary shear zone. Power equal to Fv. Fv meaning Fsvs, because this is the primary shear zone. Then Fsvs, Fsv we know and Vs we know. Then you can obtain the power here. Power to overcome the friction, also to overcome the friction here, meaning Fvc in this direction. Then also can be obtained as Fvc, or you can just obtain the power equal to Bs divided by plus Bf. Then power equal to Fcv. We know Fc and V. Then you can obtain the power, and then you subtract the power, you subtract the shear, then you get the friction, or friction equal to Fv directly. Then you can obtain material removal rate equal to WTOV. or VFD. Then same meaning, all is given, then you can obtain. Unit power also can be obtained. If ask you what is the unit power equal to the BC that we have already here, this is the BC, or power, the main power, divided by material overhead, then you get unit power of this material. This is example, right? Next problem 2. I really recommend you to practice by hand. I recommend you to practice by hand. You must practice by hand. Don't just rely on understanding. This is not enough. I'm telling you, this is not enough. You must get the calculator and you must practice by hand and solve it by yourself. Don't see the answer, the solution. Just try to do by yourself. And later you check your answer by the solution. If you find something wrong, try to find what is the wrong and what is the issue. And then you try it until you get familiar with how to solving this problem. Otherwise, you come to the exam, you will have problem to solving this kind of numerical problem. Let me read problem 2 together. In a turning operation, this is a turning operation. Cutting speed is given. This is a V. Cutting speed is given. Feed is 0.3 millimeter per revolution. This is a feed. When I said feed 0.3 millimeter per revolution, this is a TO, right? This is a feed millimeter per revolution, meaning that this is a TO. TO is a millimeter per revolution because the tool, all time remember, feed is a TO. Feed millimeter per revolution is a TO because tool cut the TO here, this is a TO, cut TO here, and another revolution cut another TO and another TO and so on. Then feed millimeter per revolution, this is a TO. Depth of cut is a width of cut. This is a depth of cut, this is a depth of cut, and width of cut also as well. This is a width of cut also as well. So this is a width of cut and depth of as well. Rake angle is given after cut deformation shape 6. This is a TC. TC is given here as 0.5. This is a TC. And we know the TO and we know the TC determines the shear plane angle, shear strain, and material removal rate. First one, shear plane angle. Shear plane angle, this is phi. We need to know obtain the phi. Then tan phi equal to r cosine alpha divided by 1 minus r sin alpha. R, we don't know r. Then r equal to TO divided by TC. TO here, TO is please remember, TO is 0.3, which is a feed millimeter per revolution. This is the TO. Then 0.3 divided by TC 0.56. Then you get the R, and then you can apply, you get tan phi. Then you can get phi. Shear strain, this is the equation you apply and find material removal rate VFD. Then you can obtain material removal rate, right? Problem 3. The shear stress. Here given shear stress of a certain workpiece. Then even without continue reading, if he give me shear stress all time, remember, if you given shear stress, then he will ask you about the shear force. Probably will not ask you about the shear force, but maybe ask you about the cutting force, and never just talk about shear. Then in this case also you have to obtain shear. As long as the shear stress is given, then the only way is to obtain the shear force, and then after shear force you can obtain cutting force, tangential or thrust, and so on, right? An orthogonal cutting operation performed with the tool, rake angle is given, and following cutting condition, cutting speed is given, ship thickness before cut, TO is given, and width of cut is given, and cutting ratio is given, R is given, right? What is the shear plane angle? The first one, shear plane angle, is R is given, cosine alpha divided by 1 sin alpha. Then this one already done. Second question, what is a shear force? Probably I will not ask you this question, what is a shear force? I will not ask you just directly what is a cutting and thrust force. In this case even didn't ask you about this one and ask you what is the cutting and thrust force, then first you must get shear. You must first get the shear force. This is the only way. Why the only way? Because here given is a shear stress. Shear stress is given, then shear force equal to shear stress multiplied by AS. And the AS equal to WTO divided by sin phi, WTO divided by sin phi. Then you must get AS, and then you get shear force. Once you get the shear force already, then cutting force can be obtained from the merchant circle, then cutting force and also thrust force can be obtained. This is a force equal to Fs, and both can obtain as a function of cutting S from the Martian circle. Then this is a way actually. This is a way. Then you need to obtain beta. Beta can be obtained from this relation because here this one can be obtained as a function of beta, alpha, and phi. Then alpha and phi we know. Then beta we need to know obtain beta. Then beta can obtain from this equation. Then you can use this two equation to apply to obtain the FC and FT. Right. And finally, friction force needed. What is a friction force? Also, friction force can be obtained from the Martian circle or equal to Fc sine alpha plus Ft cosine alpha. This is one way. Another way also F can be obtained from the Martian circle as we described earlier. So probably you can obtain from the Martian circle. Last is the turning is performed in a work material with shear stress is given. This is a shear stress. Again, and again, shear stress, then you get shear force. The following condition use VFD. And Drake angle is given. Result shape ratio R is given. Use the orthogonal cutting will determine shear plane angle. Same, exactly same. Shear force as in cutting force and feed force. Exactly same as the previous example. So this is the end of chapter 17. Any question, guys? Generally, any question about chapter 17? Any question? Okay, so no question, meaning this is the end of chapter 17. Okay, then as you can see here, we already finished introduction and economy, material casting. Casting already finished, chapter 7 and chapter 8. Joining and welding already finished, chapter 25, 17, 26. Now we're discussing about material removal processes. Chapter 17 already finished. And now we're going to talk about chapter 18. Still remaining in material removal, chapter 19 is still remaining. Right, chapter 18. In chapter 18, we're going to discuss about 18.1 in a book, 18.1, 18.2, 18.3, 18.4. Items is machining and bar geometry, turning and related operation, drilling and related operation, milling. This is the item that we're going to cover here in chapter 18, right? This is the machining. Machining actually we have a tool, we have a workpiece, and we have a relative motion. Machining in a very simple way to describe machining: remove part of material, remove part of the workpiece material to obtain the desired geometry. You remove part of the workpiece material to obtain the desired workpiece geometry. There are a tool, there are a workpiece, and there are a relative motion between tool and workpiece to cut part of the workpiece material. This is the machining. This is a simple way to describe machining. In machining, we produce either rotational part. In machining, we produce either rotational part or non-rotational part. Rotational part, cylindrical shape, as you can see. This is whatever we call turning operation, and then non-rotational part, this is a milling operation. This is a milling machine. We produce, please remember that, this is very important. We use a turning operation to produce a cylindrical shape part, and we use non-cylindrical shape. We produce non-cylindrical shape by using whatever we call milling machine or milling operation to do non-rotational part. Either by generating or forming bar geometry. Either by generating or forming geometry. Let's see what is that mean. Okay, this one initially generating shape. Generating shape, actually, when you say generating shape, we use a tool. This tool is a general tool. This tool is a general tool. Can you see that? It is a general tool. There are a relative motion between tool and workpiece. However, to generate a shape, tool have to move. Tool have to move. So we have speed and feed and depth of cut. Initially, tool penetrate to get the depth of cut. This one is rotating. This one is rotating. Workpiece, for example, is rotating to provide the cutting speed. Tool penetrate to get the depth of cut, and tool have to travel in a linear direction or axial direction, as you can see here, to cut the workpiece material from beginning to the end. So generating shape. So you can see that tool generating shape, moving from beginning to the end. Here, tool moving from beginning to the end. Also here, tool generating shape. Tool start here, and tool moving in this direction. Tool moving in this direction, right? So tool also generating, tool moving in this direction, then tool cut the material from beginning to the end, then generating the geometry, generating this also tool moving in the contour. So tooling in the trajectory to the path here to cut the shape, as you can see. So we call it is a generating shape. This is a tool. Tool is a general tool. We use a tool to cut anything, and tool have to travel to generating shapes. This is the one. Second, we call it forming to creating shape. In this case, a little bit different. What is the difference? The tool here in this case, which is forming the shape, the tool have a certain form. That's why we call forming. The tool here have a form. This is a tool. Can you see that? This is a tool. The tool have shape, not general tool. It is not general tool anymore. This is tool design the tool design specifically for this job. The tool design specifically for this job, only for this. Aman will ask me if I would like to manufacturing another shape, then this tool cannot be used anymore. You must create another tool. So this tool not general tool anymore, but the tool is specifically designed for this shape. Then tool approach, not traveling. There are no traveling here, but tool approach. Tool here move in the radial direction. Tool will move in the radial direction to form, not generate, but form the shape, as you can see here. This one also we call it broaching tool. Broaching tool have a certain shape. Finally, a cut slot in a workpiece in this way. Then tool move in this direction. Similarly, the tool move in this direction. The tool move in this direction to cut the workpiece to create this one. If you would like to create something else, this tool cannot be used. You must have different tool. So this tool only to create this one. If you would like to create something else, different shapes, then this tool cannot be used. You must have another tool, different tool. This one also drilling is considered as a forming tool, because here if you would like to drill, for example, 10 millimeter diameter, you use the tool 10 millimeter. If you would like to cut 12 millimeter, this tool cannot be used. This tool cannot be used. You must bring another tool with a bigger size, 12 millimeter. Smaller or bigger, then different tool must be used. So we consider drilling is also forming tool, or form to create a shape tool, right? There are whatever we call is a combination. Some tool have a combination between generating and forming. Like what? Like threading. Threading means create thread. Here, this tool creating thread. Actually, initially we forming this kind of shape. This is very special tool. Have a certain angle to create the shape of thread, to generate and create. This is combination, because initially it is forming shape, and then the tool move. It is initially forming and then travel in this direction to what? To create, to form and create. Initially form, second travel in this direction to create the shape everywhere from beginning to the end. So you can see this what combination between forming and generating. This one also initially this one forming, because it is this shape forming this kind of slot. We call it T slot. This one forming T-slot, but it travel from beginning to end to create this kind of shape from beginning to the end until the end of the process. Right, so it is kind of forming and generating together. This whatever we call combination between forming and generating. Okay, I will start, or we will start here in this chapter with the turning operation. As I told you, we're going to focus on turning, drilling, and milling. Three operation we're going to focus here in this chapter, which is chapter 18. Three operation: turning in order, turning, drilling, and finally we'll discuss about the milling. We will start first with the turning operation. And turning operation to manufacturing, please remember, we call it lathe machine or turning operation, which is a single point cutting tool. Turning operation is a single point cutting tool. This one to create cylindrical shape workpiece, cylindrical all time. Turning to create cylindrical shape workpiece. So always cylindrical shape workpiece, different processes can be done. This is a workpiece. We fix workpiece in a chuck. This is whatever we call as a chuck. As this one is rotating, workpiece is rotating. This is a tool. It is a single point cutting tool. And then tool penetrate and travel and somehow to cut the workpiece material to create cylindrical shape. This is the turning machine. Not only that, but also do facing, contouring, chamfering, cut off thread. Do you remember? I hope you remember that I saw you a video before about that. We'll discuss this one again here. I will show you again a video. Let me share the video to remind you about this one. Just give me a second to hopefully remind you about the machining process could be done by using okay, why it's not working? I don't know. I'll try again. Oh, okay. Yep, right. Do you remember this video? This video we saw together before. You can see that several operation could be done in a turn. This is a turning operation. A turning operation, cylindrical shape. All time, remember, is creating. This is a single point cutting tool. This is a facing. This is a facing. We create. We cut the face here, right? This here also in turning operation we can drill. This is a drill bit tool we put in a tailstock. This is the tailstock, and this is the internal turning, right? This is the internal. This is the taper, actually taper. This is the straight cut. There we have a taper cut. This is a straight cut. And you see the big thickness here. This is the straight. This is the taper. This is the straight, right? Straight cut. This is a big thickness. This is a rough cutting. We're removing a big amount of material. So cylindrical shape. Can you see that? This is the taper cut. This is the taper. This is the facing taper cut. This is the facing, right? This is the finishing now, and this is that. This is a taper, this is a straight, this is a taper, this is a straight with a small depths of cut, small feed rate, and the higher cutting speeds, then you can just do finishing cut. So all time cylindrical shape, as you can see here, all time this process turning, this is a turning operation. Turning operation, cylindrical shape. And you see that cylindrical shape. Workpiece here is rotating all time. Workpiece tool is not rotating. Tool is not rotating. Actually, workpiece is rotating. This is the threading. Threading here, generating and forming. Forming and generating. We form and generate, as you can see here. And now we need to cut. I believe you remember this one. I saw you before. This is not the first time. I saw you this video before. Then the tool here, this one will rotate. Now is rotating. This is a tool. This is a tool penetrate in the radial direction to whatever we call it the cut off. Cut off to separate the workpiece material. Right. Then relative motion. There are a relative motion, all time relative motion between tool and workpiece. Then you can obtain whatever as you can see here. And then drilling the other side, drilling here, and then also you see here, this is the internal. Whatever you do outside, external, you do internal. Whatever you do in external turning, you can do in internal turning. Whatever is taper here, this is a taper. This is a straight cut. This is a taper cut. Also can do threading, outer surface threading, inner surface threading. So whatever you do in external surface, you can do also in internal surface. Right. So this is a creating thread. Creating thread. Can you see that? This creating thread, internal thread. Right. Okay, this is generally is a turning operation. This is generally is a turning operation, and then here you see this is straight cut, this is straight cut to clean. This is grooving and so on, what we discussed before, right? Right. So go back to the slides again. This is a turning operation. So turning operation all time. We call it lathe machine or turning operation. Do facing, contouring, chamfering, cut off, thread. This all time creating cylindrical shape. Creating. This is several operation. This several operation could be done in a turning. This is single point cutting tool, and this is several operation. This is a machine. This is a machine. A typical turning operation or turning machine. This is a turning machine. This is whatever we call tail stock. This is the tool post. This is a carriage to travel here. This is the ordinary turning operation. This is the ordinary turning operation. This is the tool. This is a chuck. This is a chuck. This is a workpiece. This is a tool. This is the tool post. This is a carriage. This is the feed drive spindle or power screw. This is the tail stock, which is another center to hold the workpiece. This is the headstock, and in a headstock, when you open it, find the gear inside, which is the gearbox is inside. This is a typical lathe machine. This is a typical lathe machine. And in turning operation, you see that what happening, you penetrate first, you penetrate, initially you penetrate. This one is rotating, all time workpiece is rotating, you penetrate to get the depth of cut, and then tool travel in linear direction, longitude, in axial, this is the axial direction. I hope you remember, then tool travel in axial direction here. Tool travel in axial direction to, this is a feed, tool travel as a feed, axial direction to cut the material from beginning to the end. This is a turning operation. Several operations could be done in a turning machine, which is a straight cutting. I believe you remember now, straight cutting. This is a taper cutting, tool travel in radial and axial simultaneously. This is a contouring or profiling. This is a groove, external groove. This is a straight cut, this is groove. This is a facing, tool travel in only radial direction. This is the groove to create groove here like this. The tool here creating groove or face groove, as you can see here. Another operation, this is a cut off tool, penetrate in radial direction to cut. Threading here tool is a special tool being used to make thread in a workpiece. This is internal. As I told you, whatever you can do external, you can do internal. You can enlarge the hole, you can threading internal, you can make taper internal, and so on. We call it boring. Internal turning, as you can see. This is the internal turning. Can you see that? This is the internal. We call it boring. Boring, the word boring means enlarge the diameter. Enlarge the diameter makes the diameter bigger diameter, right? We call it boring. And then also forming. This is a tool have a certain shape. This is a tool have a certain shape to do forming, right? Also, we can do drilling in a turning operation. But we put the drill bit in the tail stock. This is a tail stock. This is a chuck. This is a workpiece rotating, and then we put the drill bit in the tail stock here. Can you see that? This is a drill bit we put in the tail stock, and then we can do drilling by using a turning operation. So using turning machine, we can do drilling. So we can. This is also another way. This is the kerneling. Kerneling is, let me tell you, the kerneling is, this is a kerneling. Kerneling is roughing the surface. Actually, kerning operation, no cutting. It's a forming operation actually, but done in a lathe machine. There are no cutting here. We'll not do cutting. Actually, no material removal in the kerneling. And the kerneling being used to rough the surface. To make surface is rough. There are to create a pattern on the surface for handling like knopping and so on. And we use a special tool to make kerneling, and no removal, no material removal here. It's just a creating or forming shape, but we consider as part of machining, but no cutting. Yes, Abdullah, I'm listening.
To make a thread, is it forming or both? Forming
Generating and creating. No forming. Yeah, it is forming and creating. It is mix. We here form the shape. We form the shape because the tool here have a special dimension. And I mean threading tool, it's have a 60 degree. It must be standard tool. To form, we form initially the one piece, and then moving in this direction to create on all the tool. Right? It's mix. Right? You get it?
Yes.
Yeah. Oh, this is a processes could be done in a lathe machine. I hope you understand. This is a typical machine. This is a typical machine. Again, this is the tail stock. This is, remember this is the head stock. This is a tail stock. This is a tool post. This is a carriage. This is a bar screw. This is a typical. This is a spindle. This is a typical lathe machine. This is a photo actually. This actual photo. This is the actual photo of the tail. I believe you saw this one in a workshop. Did you? I believe you go to the workshop, and I believe you got the chance to see the lathe machine. This is not the first time. This is a tail stock. This is another center. It's like two center to hold the workpiece. This is the tail stock is one center, and chuck is another center. You put the workpiece between these two tools. This one mainly to supporting the workpiece. This is a carriage. This is a tool post. This is a carriage. This is a way slide way. This is a power screw. This is a headstock. The gearbox is, the gear is inside. This is the spindle. This is the machine. This is the machine bed or structure. This is a typical photo of the lathe machine. Right. And now we'll talk about the holding of the workpiece. Holding workpiece in lathe machine. Actually, when we come to the holding workpiece, we can hold workpiece in different way. Most common one is a chuck. Chuck is a way to hold the workpiece. The chuck, this is one is very famous, and mostly used in lathe machine. The chuck here, you can see that there are 3 jaw, 1, 2, 3 jaw, 1, 2, 3. This 3 jaw, just listen to me carefully, this 3 jaw are moving simultaneously. Then open and close simultaneously. And you put the workpiece inside, and then there are a key here. There are a key here to hold, then both close, this 3 close and open, then center the workpiece in a correct position. The center will be in the middle. This is 3, we call it 3 jaw in a chuck. This is a chuck. This is chuck is in the spindle. This chuck is in the spindle, right? This is the way actually how to hold the workpiece. However, there are some other different ways to hold workpiece. Like what? Like this one, we call it as a faceplate. This is a faceplate. A holding not non-cylindrical shape, because you see that, yes, and you told me that you said that in a turning operation we creating cylindrical, exactly, but the holding part, the part that we hold is non-cylindrical. Can you see that we cutting cylindrical shape, but the part that we hold is not cylindrical. Cylindrical like here, this part non-cylindrical. How to hold? Then we use whatever we call faceplate. We cannot hold by using chuck mechanism. But faceplate here, this one attached to the spindle, replacing the chuck. You remove the chuck and put the hood faceplate. A faceplate here, you can see that there are 4 jaws, not 3. Not 3, but 4. 1, 2, 3, 4. And these 4 jaws are moving independently. Independently mean everyone move in different way. Then why we do that? Because irregular shape. This one having irregular shape. You will ask me how to locate the center in the middle by using the tailstock. They usually use the tailstock. They usually use the tailstock to hold the center in a position and then clamp by using this 4 jaws. Then you can, in this way, you can ensure that the center will be exactly in the middle. So here you can say that this is a tailstock. This is the tailstock here. You bring the tailstock to here. When you bring the tailstock to here, in the middle, in the center, this one will ensure center will be in the middle, and then you clamp individually. Then you can clamp uncircular or non-circular or non-even regular shape or non-homogeneous shape. So we call it faceplate, right? Is it clear? Another method, we use a collet. Whatever we call it is a collet. This is a collet. This collet been used for automated machine. This is manual machine. Manual mean operator or technician have to clamp and unclamp every time, open and close. It take time, either here faceplate or this one, which is a chuck plate or faceplate. It is manually. The operator or technician have to every time remove and open and close and so on. It take time. Collet is an automated system. It is being used in some machine. We call it automated machine. I will show you a machine using collet later in this chapter, but anyway, this one will be removed and we added a collet. This one chuck plate will be removed and replaced with a collet system. The collet is this one. This is a collet and this is the sleeve. The sleeve here have a taper shape and this is a collet. Then you can see that I'll let you know sleeve have a taper shape. This is a sleeve. Sleeve have a taper shape in this way. And then collet will be like this. You push the collet inside. When you push the collet inside, this one is cut. There are a cut here and here and here. Do you know like what? Like the pencil. The pencil that you have. The pencil you have اللي هو القلم السنون يا شباب اللي معاكم. القلم السنون مش القلم الرصاص العادي اللي بيتبري، لا القلم السنون. القلم السنون اللي معاكم في الحقيقة there are a collet at the end. The collet. This is the feeding mechanism of the in the pencil. This is the feeding mechanism being used in the pencil. So this is the workpiece in the collet. When you push here like pneumatic, we use a pneumatic system to push here. When you push here, this one will open. This one will move out and open. Then you can feed the workpiece. And then when you release here, this one will, there are a spring system to bring this one inside, and then you clamp. Then you can clamp and unclamp by using a pneumatic system, which is the automated system. This one exactly like the mechanism you have in the pencil that you use. So this one automated system, mainly it is automated system different from the collet and faceplate, the chuck and faceplate. Finally is between the two center. Here this is one center. Here this is another center. This is one center. This is the center is a no chuck. Chuck replaced with the center here, and the other center is tailstock. This is the headstock. Here this is one center, another center, and it is rotating with this kind of whatever we call dog. This is a dog system mainly to transfer the power and rotate. It's another way of fixation of the workpiece. This is a different way on how to fix the workpiece in lathe machine. right. There are some lathe machine with a little bit different feature. There are a lathe machine with a little bit different feature. We call it is like we call it as a turret lathe, chuck mechanism, bar machine, automated screw machine, multiple spindle bar machine. This machine is ordinary lathe machine, but they added some modification, some improvement, some modification to make it like automated, like faster production rate, like better performance and so on. These modifications they added, they make a little bit having special mechanism for improvement, right? This is the item that we're going to discuss, which is other production turning. It is exactly turning, but a little bit modification we will discuss now. The first one we call it is a turret lathe. Turret lathe. Turret lathe here, it's ordinary lathe machine gun. This is a chuck mechanism and this is a workpiece and rotating. Everything is same, except here there are a tailstock. The tailstock being removed. Tailstock is removed and tool post also is removed. This is a tool post actually. Suppose we fix tool here, we remove the tool post and put the turret. This turret is indexable. Indexable means it can rotate. This turret can rotate. Can rotate mean like here. You get one tool, if you rotate in this way, let me just highlight, the turret rotating in this direction. For example, when turret rotate, another tool, you get another tool, another tool, another tool. It's kind of you setting a machine beginning before you do machining, and then it's quickly, instead of every time you have to clamp and unclamp the tool and so on. No, here, this one, it's kind of automation, a little bit automation added here for faster production rate. So tailstock replaced by turret, also tool post is replaced with the turret, and tool rapidly brought into the action by index the turret. Application for high production work that require sequence of the two cut tool. I mean that not only one, we need to do several operation. Mainly you need to do several operation for one workpiece. For one workpiece, several operation with several tools. Then probably this one help to produce or quickly producing or several, I mean do highly production cutting. The next is the checking mechanism. We call it as a checking mechanism. Here you can see the tool post replaced with the CNC head. The CNC cutting head here. Then this one, no tailstock actually. No tailstock. Tailstock is removed here. Workpiece will be held by a chuck. Then this one usually short, lightweight part. No long, because if you would like to have a long hair, then tailstock needed to support. But in case of you have this case, then shorter workpiece, lightweight and shorter workpiece could be used. And then here, use a chuck here to hold, and no tailstock, and part cannot be mounted between the two center, and the cutting action controlled automatically by the CNC head. Cutting action controlled automatically by this one is rotating to bring several tools. So one tool, another tool, and so on for cutting. This is for high production machining. This modification done for high production machining. Next is bar machine. Bar machine, actually we replaced the chucking mechanism with the collet mechanism. We remove the collet, which this is let me tell you just a second. We actually here change this is a chuck mechanism. We remove the chuck mechanism and we replace with the collet for automation. As I told you, this is automation feeding system. You can see this is whatever we call multiple bar machine. This is multiple bar. This is 1, 2, 3, 4, 5, 6. This is multiple bar, and everyone have a collet. This is one collet, another collet. Collet like exactly like the pencil here. We're feeding the workpiece from the back. We're feeding the workpiece from the back, and collet open and close by pneumatic. Pneumatic system يعني هواء يا شباب. إذا كلمة pneumatic باستخدام الهواء المضغوط. So by using a pneumatic system here, we're pushing this collet to open and close. When open, then you can feed the workpiece. When closed, then clamp. Then how many bar we have here? 1, 2, 3, 4, 5, 6 bar actually, and everyone there are a different tool. This is 1, 2, 3, 4, 5, 6. Actually, this one index rotating. This one rotate. This is a collet mechanism. Let me tell you, this is a collet mechanism. This is a pneumatic system here. This is a workpiece. We're feeding a workpiece. This one we push like this. We push like this to feeding or to clamp and unclamp. So we push and open to open and clamp to feed the workpiece. To feed the workpiece, we push like this to open and feed the workpiece, and then we bring back to clamp and then being used in a cut. And here we have a several tool corresponding. Every bar, we call it bar here, corresponding one tool is located at every bar to do certain cut. How it work actually? It work like this. We call it 6 bars. This is bar number 1, this is 2, number 3, number 4, number 5, number 6. So we have here, you can see that 6 bar, and this 6 bar actually 6 workpiece. And at every workpiece located there are one tool. This tool to cut certain cut, another tool, and this one is rotating. When finished, then 1 become 2, 2 become 3, 3 become 4, and so on, and then you get sequence. Yes, Ahmed. I'm listening. Any question?
Yeah, Dr. What just I pressed for the attendance. I couldn't press yes, it just disappeared. Oh, I
Okay,
don't
no
know.
problem. Did you check the first one? First
Yes.
attendance?
Yeah.
Then should be fine.
Okay. Thank
Okay,
you.
guys, this is, I'll stop here recording.